Exercise 6 summarizes different concepts about correlation and regression. Here we have a data set that relates cigarettes smoked a day with life expectancy. Here we have the scatter plot. Question A. What are the explanatory and response variables? This is easy. The explanatory variable is number of cigarettes smoked a day. The response variable is life expectancy. Question B. Describe the direction, shape, and strength of the relationship between cigarettes a day and life expectancy. Remember that you cannot answer this question by just looking at the table or the correlation coefficient. You need to get the scatter plot. In the scatter plot, we see that this relationship is negative, linear, and strong. Question C. Use a statistical software to find the equation of the regression line between cigarettes a day and life expectancy. The regression line is the line that best fits the data set. We could call it the optimal line. I have created tutorials where I teach how to use a statistical software to obtain things like this. Watch my tutorials if you need to learn how to use the software. With the software, you will see that the equation of the regression line is this. Usually, books and softwares don't show this predicted. I like including it because the regression line is just a mathematical model, it's not the reality. What we get with the regression line are predictions. It's always a good idea to sketch the line in the scatter plot like I did here. Question D. Interpret the slope. A silly mistake that I see here very often is writing only the number, negative 0.696. This is the slope, yes, but you are asked to interpret it. So how do you put this number into a sentence? The general algebraic interpretation of a slope is the increase in the y per each unit of increase in the x. Since the x here is number of cigarettes smoked a day, and the y is life expectancy, the interpretation would be, per each cigarette smoked a day, the life expectancy is expected or is predicted to decrease by 0.696 years. Again, I am including here the expression is expected or is predicted because this is not the slope of the reality, it's only the slope of our mathematical model, the slope of our predictions. It's a sort of average of what we observed in the sample. Notice that here the word decrease replaces the negative sign and we write then the absolute value of the slope. Question E. Interpret the y-intercept. The general interpretation of a y-intercept is the value of the y when the x is 0, that's to say in the origin. Very often, the interpretation does not make sense for a regression line because the 0 is too far from the data set and it might be kind of absurd considering x equals 0. But in this case, it does because a person can smoke 0 cigarettes a day. The y-intercept here is 84.76 years. So the interpretation would be the life expectancy of a non-smoker is expected or predicted to be 84.76 years. Question F. Find the correlation coefficient and interpret it. You do this with a software. It is negative 0.83. The scatter plot shows that the relationship is linear, so we can interpret the coefficient in this way. The relationship between cigarettes smoked a day and life expectancy is negative, linear, and strong. Question G. Find the coefficient of determination. Interpret it. The coefficient of determination is simply the square of the correlation coefficient. In this case, it is 0.69. Here a warning. Usually, it is completely different from the slope. In this particular exercise, coincidentally, they are very similar. Many authors interpret the coefficient of determination as the proportion of the variation in the response that can be explained or predicted or determined by the explanatory variable and our mathematical model. In this case, we can say 69% of the variation in life expectancy can be predicted or explained or determined with the number of cigarettes smoked a day and our linear model. In other words, it's clear that life expectancy varies. For some people it's 78 years, for some other people it is 60 years, for others it is 55 years. What are the factors involved in that variation? There is one factor that is so involved as to let us predict or account for 69% of that variation. That's to say, a great majority of the variation. And this factor is the number of cigarettes smoked a day. What happens with the other 31% of the variation? There are other factors or confounding variables involved in life expectancy. Maybe we could predict or explain or determine more of the life expectancy's variation if we considered these other factors. What I don't like about the expression explained by is that it seems to imply causation, and the coefficient of determination has nothing to do with causation. That's why I might suggest to better use the verb to predict or to determine. By the way, using the verb to determine makes sense of the name of the coefficient. Question H. If a friend of yours smokes 29 cigarettes a day, what's the prediction of their life expectancy? This is the kind of question that we answer with the regression line. The value of the explanatory variable is given. We plug it in the equation of the regression line and it gives us the value of the response, 64.58 years. We were anticipating a low life expectancy because this friend smokes so much. Interestingly, the 29 was one of the values in our sample, so we can compare this prediction with the actual observed value. This brings question H and the concept of residual. Notice that the life expectancy observed in the sample for 29 cigarettes a day is 58, even lower than our prediction. The definition of residual is the observed value minus the predicted value. The observed value for 29 cigarettes a day was 58, minus the prediction given by the regression line equals negative 6.58. We can graph this residual in the scatter plot. For 29 cigarettes a day, the point in the regression line is the prediction, and the point in the cloud is the observation. This difference or distance is the residual. It's important to speak of these residuals because minimizing their squares is the criteria with which we select the optimal line, the regression line. In other words, you could think that maybe a line like this is a better fit because it crosses more observations. Certainly, the residual for these observations would be close to zero. But if you consider all the other residuals squared, you will accumulate more error with this line. In this criteria, we square the residuals to prevent the negative ones from cancelling the positive ones, same as we do in the standard deviation as we saw in Chapter 3, Part C. So you can bet that this line, the regression line, is the optimal line for this dataset. Optimal according to what? According to minimizing the sum of squared residuals. As a final idea, this sum of squared residuals is used also as a measure of appropriateness of the model. That's to say, if you use that criteria to find the optimal exponential model, you will see that that optimal exponential model generates a greater sum of squared residuals than this linear model. It seems clear in the scatter plot that this is more linear than exponential, but the sum of squared residuals provides a numerical measure of that. Question J. Could we predict the life expectancy of a person who smokes 65 cigarettes a day? You can always plug the value in the equation of the regression line. The problem here is that the highest value of the explanatory variable in our data set is 43. If we predict beyond this point, we are assuming that the pattern continues the same way, but we don't know that, so we cannot trust much this prediction. This is called extrapolation, predicting beyond the range of our data, and it is always less reliable than interpolation, which means predicting within the range of our data. The classical example is the relationship between age and height. It is positive, linear, and very strong from 3 to 16 years old, but we cannot use that regression line to predict the height of a person who is 40, because the pattern changes drastically after 17. People stop growing. The prediction for the 40-year-old guy could be 10 or 12 feet or 3 or 4 meters. This is another reason why the y-intercept usually doesn't make sense, which we mentioned in question E. When the zero is far from the dataset, it usually happens that the relationship is very different close to the zero. Question K. Does this study prove that smoking reduces life expectancy? What lurking variables could explain the observed relationship? The first answer is obviously no. Correlation never proves causation. This reminds you of what we saw in Chapter 1, that an observational study can never prove causation. The second question introduces the concept of lurking variable. For many authors, it's just a synonym of confounding variable, which we also saw in Chapter 1. Interestingly enough, they tend to introduce them in different moments. They usually speak of confounding variables in the context of experiments, and lurking variables in the context of correlation. It seems to me that it is more common to call confounding variables, or confounders, to those variables that operate over the response together with the explanatory. This is the diagram that I used in Chapter 1. Then I defined a confounding variable as any variable that could affect the response and is not the explanatory. But the confounding variables don't need to affect the explanatory. They are just there with it. A different structure is this. When we have a variable that affects both at a time, the explanatory and the response variables. In cases like this, the explanatory and response variables change together, not because one is the cause of the other, but because there is a third one causing both. A nice example that a colleague of mine uses is when his boy was born, he planted a tree in their backyard. During the first 8 years, the correlation between the height of the tree and the height of the boy was almost perfectly linear, with a correlation coefficient of almost 1. But neither the tree was responsible for the child, nor the child was responsible for the tree. So what variables could explain the strong correlation? Probably the most important is time. Since time passed for both and both were living beings, they grew together. We could also mention the father. The father was taking care of the tree and the son. It seems to me that the concept of lurking variable is most often used in situations like this, where one variable is hidden, affecting both the explanatory and the response, like a puppet master. Anyway, since these two terms are commonly used exchangeably, you might be entitled to use the one you prefer. Just in passing, this example of the tree and the boy is a good moment to bring back the concept of coefficient of determination, which we introduced in question G. It was also very high in this case, let's say 0.95. The question that this coefficient answers is how much of the growth of the boy can be determined if we know the growth of the tree. The answer is a lot. If you tell me how tall the tree is, I will put this height in the regression line and I will tell you almost exactly how tall the boy is. So the interpretation of the coefficient of determination makes much sense here. 95% of the growth of the boy can be determined with the help of the tree and the regression line. Again, this does not imply that the tree is the cause of the boy's growth. Going back to question K, some lurking variables that could explain the correlation between cigarettes smoked a day and life expectancy are lifestyle and mindset or personality. Let's say that John is committed to a healthy lifestyle. Because of this, he does not smoke, but also because of this, he takes care of his diet, he exercises regularly, and all this may also increase his life expectancy. One final thought. Here we are not saying that smoking cigarettes does not reduce life expectancy. What we are saying is that this cannot be proved with just a correlation.